Okay, so the recording has started. So welcome everyone for the second session of this LQG summer school today. We will be listening to Ivan Agullo on quantum field theory in curved space-time. So as before, if you have a short clarifying question, you can ask them in the chat and I will moderate them. Otherwise, you keep them for the end and we will have 10 to 15 minutes to ask them. So Ivan, your turn.
Thank you, Pierre. So welcome back, everybody. So this is the second part of my presentation. And let me start with a summary of what we discussed yesterday. Remember that my goal here is, is just to give you a lot of information in a short amount of time, because, these mini courses are like that. The goal is that you see all this information flying in front of you and you will retain something, but more important, you will be motivated to go and learning by yourself. And this is my main goal, to motivate you. So remember field theory, the classical field theory can be formulated as a theory of symplectic geometry. We are dealing with linear systems here. So the vector space is a linear vector space, and it is equipped, it is infinite dimensional because this is a field theory, and it is equipped with a symplectic structure that has two indices downstairs. Observables, linear observables, belong to the dual of the vector space. They are linear functions on the phase space, and they satisfy this algebraic relation given by the inverse of the symplectic structure. And in fact, what we can do, and we did, was to define these two observable value distributions, phi and pi. I am in the classical theory, so I shouldn't have a hat here. That is a typo. So phi and pi are not observables mathematically, but if we smear them with test functions, they become observables. So they are observable valued distributions. And smearing them, this is where I denote by this contraction, we get observables. Remember, this contraction contracts the index 1 and 2 for the phase space field and momentum, and also the index x. So there is an integral involved in this contraction. Quantum theory is rather a Scalar theory of Scalar geometry. Remember to move from a symplectic phase space, vector space to a Scalar vector space, we need to include one extra ingredient that can be either a complex structure or a bilinear, which is symmetric and positive definite. I call this metric because mathematically it's like a metric, but here is not the metric of a space-time or nothing like that. It's just a symmetric and positive definite metric matrix in the phase space. And they have to have some compatibility. A complex structure needs to define G and vice versa. And as we discussed, this is equivalent, the introduction of either of them is equivalent to take the complex phase space, the complexified phase space, and divide it into subspaces. One I call gamma plus, in which the symplectic product is positive definite. And the other, gamma minus, is just the conjugate, and the symplectic product is negative definite on it. And the good part is that now we can build a Hilbert space out of gamma plus and a Fock space. So, and you see the relation, each of these elements define the other. For instance, if you give me gamma plus, I can build a basis of vectors in gamma plus. It's infinite dimensional because we are in field theory, and just doing linear combinations of products of the basis elements in this way, where this parenthesis is the symplectic product, or in this way, you get either J or G. So you can see the relation, the arrows go in both directions. And this is useful at the practical level, because if you give, normally at the practical level, it is many times easier to identify gamma plus than to introduce a J or a G. So if you give me gamma plus, you can use these relations to obtain the J and G that corresponds to that gamma plus. So we close the circle. Then once you have gamma plus and a basis, I show you how to get a representation of the elementary operator value distributions in the quantum theory. You just need to take the sum of basis elements times their creation operator plus their Mission conjugated, because the fields are real. And that is a representation of the operator value distributions. In addition, I have evolved the basis elements in time using the classical equations of motion, and that automatically gives me the Heisenberg version of the operator value distribution. So in this simple way, once you give me gamma plus and a basis, I can write the Heisenberg representation of the operator value distributions. And of course, smearing them, taking linear combinations of them, I get any linear observable. And here I am writing explicitly this contraction. So you remember that there is an integral involved. So the most general linear observable in the Heisenberg picture here is a smearing of the field and the momentum operator valued distributions. And in this way, we have a representation for all of them, and they satisfy the appropriate commutation relations. From here, the vacuum state is the state annihilated by all the annihilation operators. And acting on it with the creation operators, I get number states, and they span the Fock space. Technically, they span as a dense subspace of the Fock space, because remember, in infinite dimensions, we need always to Cauchy complete the vector space to have a Hilbert space. But these are mathematical details. And the vacuum is a quasi-free Gaussian state. So it's always a Gaussian state with zero mean. And evolution preserves Gaussianity. Linear evolution preserves Gaussianity. So the vacuum is always a Gaussian state, quasi-free, and fully characterized, therefore, by the covariance matrix. But the covariance matrix, the matrix of the second moments is precisely this metric that defines the Fock representation. So in this line, you see this relation between the mathematical aspects of the Fock representation, this metric or complex structure, and the properties of the Fock vacuum, the 2-point function, the symmetrized 2-point function of the Fock vacuum. So this is nice. And this is all what we need to do physics. You give me a quantum state, and then I can compute any expectation value that you ask me and any evolution. So this is the theory in this slide. Yesterday, I was a bit more detailed, and I was showing you how to build the Fock space, how to give you a functional representation, how to build the Fock space from the elements of the phase space itself. But I told you that I use that, to think about the theory, but to compute, I use just Brass, and Katz. And this is similar to what we do with the harmonic oscillator in elementary courses, right? In elementary courses, you first derive the harmonic oscillator and the Hilbert space using Hermite polynomials, these horrible long polynomials, and annihilation and creation operators are differential operators on them. But then you learn how to encode them in Brass and Katz, and you forget about Hermite polynomials. Here, it happens the same. We have in mind that there is a concrete Fock representation based on the elements of the phase space themselves. And if you ask me to prove a theorem, I will use that. But to do calculations, I use Brass and Katz, creation, annihilation, and precisely what I have in this slide. This is what I use at the practical level. So it's good to have both in mind. Okay, and now to continue with yesterday's lecture, let me summarize the very last thing we said. The last thing I described was about the ambiguity in this contraction. So the ambiguity happens similarly to the finite dimensional case, and is that in arbitrary spacetimes, there is no preferred choice either of complex structure or G or vacuum. In general, there are infinitely many choices, different choices available, and all of them are at the same level. So, you know, and this is the way it is. And we need to accept it. So if you ask me, what is the vacuum? I will tell you, I mean, there is no a vacuum. Vacuum, you know, doesn't have any, it's not physically preferred unless you have symmetries. It's just, you know, this Fock vacuum in a concrete Fock representation, and depends on your choice of Fock representation. And the same with particles, because particles are, you know, they arise by acting on the vacuum with the creation operator. But if the vacuum is ambiguous and the creation operator is ambiguous, what you mean by a particle is also ambiguous. And that is shocking because we don't see that around us. If around us, we know what an electron is. But if we take, you know, because the space-time in this room is very close to flat space-time, and we don't notice. But if we take bigger regions where the curvature is important and the space-time is time-dependent, then if you ask me what an electron is, I would say I don't know what you mean. You give me a Fock representation, and I will tell you, you know, what is an electron on that Fock representation. But that depends on your representation. And that is fine with physics. There is nothing wrong in that. The field theory makes perfect sense, but we don't have a preferred or privileged Fock representation, physically preferred notion of vacuum or of quanta in the theory. So this is quite important. Quantum field theory is not anymore particle physics, but it's really field theory. And you know, just to remind your memory, imagine you give me two choices of Fock representation, you know, J or G, the basis, one particle Hilbert space, Fock space, creation, annihilation, and vacuum. How to relate them? The relation mathematically can be extracted easily at the practical level just by relating the two bases, the basis 1 and the conjugate, and the basis 2. The coefficients are called Bogoliubov coefficients. And they can be extracted just multiplying, you know, V2, for instance. If you multiply on the left by V1, you will extract alpha. If you multiply on the left by V bar, the conjugate, you will obtain minus beta, because V bar has negative norm. So just computing Klein-Gordon products between the basis elements, you can extract the Bogoliubov coefficients. And they relate the two representations in the following sense. One can check that the relation between creation and annihilation variables, operators, are given by these coefficients, except for this minus and conjugates, but it's exactly the same information. And from that, one can prove, and I didn't prove it, I just told you, that the vacuum in one representation, when you write it in the other representation, looks like the exponential of A dagger acting on the other vacuum. So if you expand this exponential, you know, vacuum 1 looks like a combination of infinitely many states with even number of quanta, 0, 2, 4, 6, and concrete correlations between entanglement between the quanta. And in particular, if you ask me what is the number of particles defined by the 2 representation in the 1 vacuum, that is given by the Bogoliubov coefficients square. So if the Bogoliubov coefficients beta, the beta, not the alpha, the beta, are different, which means that, let me go back, which means that V2 has some component in the direction of V bar 1. So the second positive norm basis has some component on the negative norm component of the first basis. If this beta is 0, the two representations are the same. But if beta is different from 0, then the two representations are different. And that is also equivalent to say that the two complex structures are different.
There is a short question, Ivan.
Okay.
Are these Bogoliubov coefficients the same as we use in the BCS theory?
Yes, they are similar. They are similar. They are just relations between creation and annihilation operators. They were introduced first in condensed matter long ago, and then Leonard Parker introduced them in the context of quantum field theory in curved spacetimes. And again, they are just linear relations between creation and annihilation variables. Therefore, different complex structures give you different Fock representations. Sorry for the displacement of the arrow. Subtlety. And this is where I stopped last day. Subtlety. In finite dimensions, in quantum mechanics, there is guarantee that any two Fock representations are unitarily equivalent. And that is guaranteed by the so-called Stone-von Neumann theorem. But that is not true in field theory. In field theory, we find that in general, two different Fock representations can be unitarily inequivalent. So, and I will tell you what that means. And there is a mathematical condition that we described yesterday. At the practical level, if the Bogoliubov coefficients are square summable in the two indices, then the two representations are equivalent. Unitarily equivalent. Not the same representation, but there is a unitary map between them. So there is a dictionary between them. And in the language of physics, as I mentioned yesterday, this means that the vacuum one has finitely many particles in the Fock space too. In that case, the two representations are unitarily equivalent. What happens if that is not the case? And this happens all the time. In fact, in cosmology, if the universe at even time is not compact, so like in a flat Freeman-Robertson-Walker, that special slices are R3, they are not compact, then any two representations happen to be inequivalent. Any. So this inequivalence appears all the time. Then mathematically, the two representations describe different physics. Because if you don't have a dictionary between them, one physical state here cannot be mapped to the other Fock space. Physical states in one space doesn't fit in the other, doesn't belong to the other state. There is no map between one and the other. So it is not clear, you cannot ask the same questions because you don't have the same states, not even a relation between them. So mathematically, the two theories are inequivalent, physically inequivalent, and that is shocking. However, this is not as dramatic as it may look from the physical viewpoint. And the reason is that you can prove this inequivalence only because this inequivalence is coming from the infinitely many degrees of freedom. If you have finite degrees of freedom, finite observables, then any two theories are equivalent. So physically, you can only prove this inequivalence if you are able to prove infinitely many observables. So if you prove your quantum state with all possible observables, then you will have to face this inequivalence. But that doesn't happen in practice. So let me summarize this. By this, but this inequivalence is considered a mathematical issue in the sense that we can restrict always to finite number of observables. If you tell me, we are going to measure only this set of observables, can be as large as you want, but has to be finite. Then for that restricted set of observables, one can always find a unitary dictionary with arbitrary precision. So therefore, the statement is that this is not considered a problem to do physics. And as long as we can only measure a finite number of things. And this is what we do, because we cannot measure a quantum state in Andromeda galaxy. We can only restrict to a finite region of our universe, and that is enough to restrict ourselves to a limited set of observables. In that case, I insist, then one can have a unitary map with arbitrary precision, even though there is no exact unitary map. And this is the way practitioners in quantum field theory in core spacetimes use this theory. But I think it's good to know both, to know what is true mathematically in a rigorous sense, and also physically how to proceed. And this is a very important message in quantum field theory in core spacetimes: the existence of unitary inequivalent representations, and also how to deal with them physically. So please retain that in your memory.
There is a question, Ivan. Is the Fock representation dependent on the choice of observers, like Minkowski spacetime, the inertial observer and Rindler observers? They have different vacuum.
No, I mean, the observables are the same. Remember, they were determined by the classical theory. We are limiting ourselves first to linear observables, and they are just given by they are established already in the classical theory. They are just one forms, dual vectors in the classical phase space. This is the family of observables. And then in a Fock representation, we represent them. In a different Fock representation, we also represent them. So, the idea is that you have these observables. We call them initially abstract operators, because initially they are just defined abstractly without any Hilbert space. But then you represent them in different Hilbert spaces, in different representations. And the statement is that if you focus on a finite family of them, and you represent both, then the predictions of the two representations are related by a unitary operator with arbitrary accuracy.
But I think the question was whether two different Fock representations can be understood as two different observers.
Observers.
Yes, not observables.
Observable.
Yeah.
Thank you. Yes. Yes. In that, two different observers, like in the Unruh effect, the inertial observer and the Rindler observer, they naturally produce two different representations. Essentially, because they follow different trajectories in space-time, and they adapt the vacuum to their time evolution, and therefore they have different vacua and therefore different representations. Thank you, and sorry for.
Thank you.
Yes, and you will see later on that when I discuss in a minute the in-out representations, they are singled out by observers, by natural observers. So that's a physical way of thinking about different representations. That's been singled out by different observers. Okay, exception. It happens that if the metric, the spacetime metric, admits a globally time-like Killing vector field, so there is a time-like symmetry, a time-like direction in which the metric doesn't change, then there is a preferred vacuum. And this is a very important box. So this tells you exactly when this ambiguity disappears, whenever you have a global time-like Killing vector field. The complex structure or gamma plus is singled out, by considering solutions to the wave equation that oscillates with positive frequency, or in phase space, the initial data of solutions that oscillate with positive frequency with respect to the Killing time, the time along the Killing trajectories. And the reason is that if you have a time-like Killing vector field, the time derivative along the Killing direction commutes with the Klein-Gordon differential operator. So you always have solutions with well-defined frequency. And then you have a well-defined notion of positive frequency subspace of the space of solutions or the phase space, as we have in Minkowski spacetime. Physically, it's normal that there is a preferred vacuum, because whenever we have a time-like Killing vector field, we can define a Hamiltonian out of it, which is time independent. And remember, if you give me remember the way to obtain conserved quantities in field theory out of a Killing vector field. You need a foliation, you need the unit normal, and then you contract the energy momentum tensor with the unit normal and the Killing vector field. And the quantity that you obtain is a constant of motion. In this case, because t is a time, this is a Hamiltonian. So for a time-like Killing vector field, you have a time-independent Hamiltonian. Doesn't matter which foliation you choose, that the Hamiltonian is the same. It's time-independent in the Killing time. And therefore, there is a ground state. And this ground state is precisely this preferred vacuum. So again, time-like symmetries in a space-time give you so message, a time-like symmetry is enough to recover a preferred notion of vacuum. A space-time-like symmetry is not, and we will see an example in 1 minute. So time-like symmetries single out preferred Fock representations, which agree with the ground state of the Hamiltonian. I don't prove this as a theorem, and I just refer you to the original reference. This was obtained by Ashtekar and Magnon in the 70s. Okay, with this, I want to finish this section of the ambiguity, the existence of multiple, different, and many times inequivalent Fock representations. Now, I want to study what I call the in-out situations. What I mean by a in-out situation, let me define what I mean by that, is I want to restrict to a special family of spacetimes, those that are asymptotically flat in the past and future. The spacetime is time dependent in general, it's arbitrary, but if you go to the future, it becomes Minkowski. If you go to the past, it becomes Minkowski. I call it in-out because we have the in and out Minkowskian regions well defined. So the space-time in general is not globally the time-like symmetric. There is no global time-like Killing vector field. So there is no a single preferred representation. But there are two local time-like symmetries, one in the future and one in the past. So, so we can choose two preferred representations. The representation single out by the future time-like symmetry, that is called the out representation, or the in representation. So the in is in the past. So you just go to the past and you choose the natural notion of complex structure or vacuum in the past. So this vacuum is what an inertial observer in the past will say the vacuum is. If you are an inertial observer in the in region and you have a particle detector in your hand, this vacuum will produce 0 detections. So this is the natural notion of vacuum in the in region, and n is the natural notion of n quanta state. But you can do the same in the future. Because the space-time is time dependent in between, the relation between in and out has to be determined. So we have also, the out vacuum, which is what, 0 particles for an inertial observer in the future. Again, both have natural physical meaning in their respective regions. So I should have here out and future, sorry, this is a typo, out, future. Okay, so now let's do physics with that. Let's assume that the field is prepared initially at early times in the in vacuum. So the in observer says the state is in the vacuum, no particles. So the in observer, right. Then we evolve the system to the out region. Time evolution appears. The question we want to ask is, how does the out observer perceives that state? For him, the state is still the vacuum, or is something different? Notice important that we are changing the question in this following sense. Initially, we are the state was vacuum for the in observer, and now we are asking what the state is for a different observer, the out observer. So we are relating observations in two different frames, if you want. Because the state is quasi-free, is a Gaussian state, the in vacuum is a Gaussian state. All properties are encoded in the second moments. In particular, we can, for instance, compute the second moments of the creation and annihilation operators of the out observer. You know, A dagger, A dagger, A dagger, A dagger. So if we have that, if we compute that, we have fully characterized what the out observer will measure, will perceive. And it's not a surprise that this can be obtained from Bogoliubov coefficients. So what you have to do is to compute the Bogoliubov coefficients in the way I told you before, with one difference. Before, we were just comparing two bases, basis 1 and 2 at the same time. Now, what we have is the in basis at initial time, out basis at final time. So what you have to do is to take the in basis, propagate it to the future, and then project on the out basis. So there is time evolution in between. And so these Bogoliubov coefficients carry the information about time evolution. And we will do an example in 1 minute. Once you compute them, it is a simple exercise to check that this matrix of second moments is given by products of the Bogoliubov coefficients. And from them, you can answer any question you want about the observations of the out observer. In particular, you can ask me, what is the number of quanta? The particle number that the out observer measures in the evolution of the in vacuum. The number operator is A dagger A, so I have to go to this component, and this is precisely beta square. But you want I and J to be the same, so this is beta square. So beta square is again the number of particles that the out observer will measure. If you are in the out region with an apparatus, this is what you will measure. Interpretation: particles have been created out of the vacuum. Because initially, if you were an initial observer with an apparatus, you will measure nothing. In the future, if you have an apparatus, you will measure particles. So vacuum becomes full of particles at late times. Of course, what you mean by particle initially and what you mean by particle finally is different. These are 0 in particles initially, many out particles finally. So don't forget that. What time evolution does is to change the question. Time evolution changes the natural question from the in questions to out observer questions, and in that sense, in that concrete sense, there is particle creation. And this was discovered and formulated in a quite amazing way by Leonard Parker in his PhD thesis. He was a student of Sidney Coleman, the Coleman that I mentioned yesterday at the beginning of the talk. Was a great particle physicist. but he was not very much interested on gravity. So Parker did his thesis in Harvard almost in isolation, and he was the father of the formulation of quantum field theory in curved spacetimes. He did it in cosmological spacetimes, and he derived in his thesis by himself this in and out picture, and he found this creation of particles would appear in out situation. So this is an example of how a PhD student can make seminal contributions and open a whole new field of research. Okay, let me emphasize the two questions we have asked yesterday and today. One is we have derived how different observables evolve in time. So if you give me an observable, whatever, position, field, smear in some region, momentum, combination, and a quantum state, how this observable evolves in time. Can be linear, can be quadratic, whatever you want. How a concrete observable changes in the course of time. But in the in-out scenario, we have also answered a different question, which is, if you tell me what the in observer measures, we have derived what the out observer will measure. And the two questions are different because here we just have a physical observable that evolves in time. And here we have, we are asking the question between the in and the out regions. Questions for the in observer, questions for the out observer. So the two questions are really different. And in fact, question 2 is adapted to prefer observers in the past and future. So question 2 can only be asked if you have preferred observers initially and finally. However, question 1 can be formulated in any spacetime because it doesn't require any observer, doesn't require any preferred set of observables. This is true for any observable. And second question is adapted to prefer observers. So these are the two kinds of questions that we answer in QFT in curved spacetimes. And normally in cosmology, we answer question 1, and I will show you an example. In the early universe, working in inflation, we focus on an observable and we see how it evolves. In Hawking effect, for instance, in the Hawking radiation, when we have a in and out regions asymptotically, we ask the second question. So it's good to have, to differentiate both of them. Okay, so now I'm gonna change gears and go to applications. But if you have any question at this moment, you can go ahead.
I think Ariadna, you had a question. If you want to, I can read the question.
Please.
So, could we also define a Hilbert space, and so that we have equivalent representations within that region, in a neighborhood of a space-time where there is a time-like killing vector, like a neighborhood of de Sitter space?
So, Ariana, do you mean when you say a neighborhood of the Sitter space, space-time, you mean space-times close to the Sitter? Because the Sitter is the entire space-time, right? So what do you mean?
In particular, I meant that in the Sitter space-time, for instance, we have a killing vector as defined globally, but the problem is that it changed signature. So I was actually wondering if we could, I don't know, take a small neighborhood where this time-like killing vector exists and doesn't change signature, and so compared to observers within this neighborhood.
Right. But the problem is that one message that one needs to understand is that vacuum states are global. Quantum states are global. if you see how we have built the quantum field theory, I took the phase space. Phase space is defined in a in a Cauchy hypersurface in the entire universe at a given time, and I choose a basis of modes there, and from that I build the vacuum. So vacuum and in general quantum states by nature they are global concepts. There is no such thing as a local vacuum, and if there is, it's just a not very useful approximation. So the answer is no. If the space-time is if you don't have a global time-like Killing vector field in a space, there is no preferred vacuum, even if there is a vector field that in some region, a spatial region, becomes time-like. But it happens that in some circumstances, like in the sitter, and I will discuss that later on, even when you don't have a globally time-like Killing vector field, still you have enough symmetries to single out a preferred vacuum. In the sitter, or in Friedman-Robertson-Walker de Sitter, the portion of the sitter that we can embed in Friedman-Robertson-Walker, which is what we use in inflation. There you have 7 Killing vector fields, and I will show you that later on. And in that case, you have enough symmetries, even though they are not time-like globally, neither of them. But you have enough symmetries to single out a preferred state, and that is called the Banch-Davis vacuum. But in general, that is not true. Vacuum states and quantum states are global entities, and this is something. This is a very important message. They are global entities.
Thank you, Ivan. You can go ahead.
Okay. So applications. This part is short, and because I thought it was going to take me more time, and so I am faster than what I expected. So that means that you can ask as many questions as you want, and you can interrupt me because we have time. So I want to give you 2 applications of this theory, which are the 2 applications of largest physical interest. What happens, in cosmology, quantum field theory applied to our universe as a whole, and what happens in the process of collapse of a black hole. So you are going to see how to apply these formulas, and this is very important because if you only know the theory conceptually, but you don't know how to apply it, you know nothing. And vice versa. If you know how to apply it, but you really don't understand what is going on, it's not good either. So a good physicist has both connections between mathematics and physical predictions. So for simplicity, I'm gonna just focus on one family of cosmological spacetimes, especially flat, Friedman, Lemaitre, Robertson-Walker. You know that many people call it FRW without the L. I will advise you against that, because if anything, L is more important than the others. Lemaitre was in my opinion, the key researcher, the key person in the development of early cosmology. Friedman was very good, even he wrote papers before him, but he didn't have the physical clarity that Lemaitre has. And Lemaitre had to find against Einstein, which was a big battle, and he won. So never forget the L. So especially flat, Friedman, Robertson, Walker. The metric is the familiar metric that you all have seen in elementary courses. This spacetime is highly symmetric. It has 6 Killing vector fields corresponding to 3 translations and 3 rotations, spatial translations and spatial rotations about any arbitrary point of a space. So this is highly symmetric. Remember, in 4 dimensions, the maximum number of Killing vector fields are 10, and we have 6 here. They form the Euclidean group. And in particular, they can be used to select a preferred foliation of a space-time. So there is only a single foliation in which the metric is homogeneous and isotropic inside the foliation. So if you tell me homogeneity and isotropy, I immediately imagine the space-time foliated in a concrete manner. And T is what we call the cosmic time, and its proper time along this geodesic time, because the coefficient is -1. For us, the scale factor A, that is called the scale factor, and tell us that the metric is not time independent, so there are no time-like symmetries, is a known and given function. And our quantum field is not changing that. We are not considering back reaction. The geometry is fixed once and for all. This is quantum field theory on a fixed curved spacetime. An example is, familiar radiation domination universe in which the scale factor grows with the square root of cosmic time. No time-like isometry for general scale factors. You need to choose A to be very special, like constant. If it is constant, obviously you are in Minkowski spacetime. For convenience, I'm going to put the universe in a box with periodic boundary conditions, box of volume V0. And the reason is because we are going to do Fourier transforms, and if the space is non-compact, the Fourier modes are not normalizable with the Klein-Gordon product. They are normalized to the Dirac delta, which is not a normalization. So, just to have more mathematical control, the trick is you put the universe in a box with periodic boundary conditions. Then the Klein-Gordon norm of plane waves is the Kronecker delta. You do calculations, and once you derive physical quantities, you take the volume to infinity at the end of the calculation when everything is under control. As you know, it's convenient to define conformal time in these geometries. This is defined by this relation between dt and d eta. There is a scale factor in between. And it's called conformal time because if you write the Friedman-Lemaitre-Robertson-Walker metric in conformal time, the scale factor factors out. So you have the scale factor times a metric that looks like the flat metric. So therefore, this shows explicitly that especially flat FLRW spacetimes are conformally flat. And this is what we mean by conformally flat. The metric is conformal, a positive factor times the flat metric. Therefore, the Weil tensor, if you compute the Riemann tensor, you will find that the Weil tensor is identically 0 because, it is always 0 in conformally flat spacetimes. All the information is in the Ricci tensor and scalar curvature. And it's an exercise to compute the scalar curvature, and it's given by dot is derivative in cosmic time. So the second derivatives of the scale factor. Remember, curvature is always second derivatives of the metric. And because here we have space-like symmetries, the only non-trivial derivatives are time-like symmetries. The coefficients of the metric only depend on time. So we just have second time derivatives. And if you did it in conformal time, this is even simpler, A prime prime over A cube. So this is the form of the Ricci scalar. Okay, field equations. You take the Klein-Gordon equation you plug coordinates, for instance, cosmic time, and then this is the differential equation that you get. You have second time derivatives, the second spatial derivatives. This is the familiar Euclidean spatial Lagrangian, Laplacian, sorry, and you have coupling to the curvature if you have in the action. And you see that the coefficients are time dependent because the space-time is evolving in time. So you have a partial differential equation with time dependent coefficients. And partial differential equations are always tricky to solve. But we know good trick because of the spatial symmetries. We can use Fourier analysis to convert this equation to an ordinary differential equation. So we just need to take the Fourier analysis adapted to the spatial Laplacian. But because the spatial Laplacian is Euclidean, the Fourier, the eigenfunctions are just plane waves. So this is the Fourier analysis that we need to do. And that is going to change this equation to an ordinary differential equation in time only for these Fourier variables phi of k. The only thing you need to remember is that the scalar field is real, but the field in Fourier space cannot be real because you have an exponential, complex exponential here. So we need to remember that there are some relations that make phi of x real, and they are this relation. The conjugate of the Fourier mode must be the negative, must be the Fourier mode for the negative k. And that is because then the exponentials of k and minus k will combine in a cosine, and you will have a real field. So we are going to work with the field in Fourier space, but never forget that this is a complex field, and these reality conditions must be always satisfied. So this Klein-Gordon equation, once you use Fourier transform, becomes this equation. And this equation is an ordinary differential equation in time. The x derivatives have been replaced by k derivatives, just because the Laplacian acting on the plane wave give you two k's multiplying each other because of the square. So you have k squared, no spatial derivatives. And this is the equation of an harmonic oscillator with a time-dependent frequency. This big parenthesis is like the frequency. And this is a friction, right? Because it's proportional to the velocity. So we have transformed a field equation into infinitely many decoupled, because different k's do not talk to each other. We have the same k in the three entries. So different Fourier modes decouple. And for each of them satisfies the equation of a damped harmonic oscillator. So this is wonderful because we know how to solve an harmonic oscillator, and we know how to quantize an harmonic oscillator. So the quantization of the field theory mathematically reduces to quantize infinitely many decoupled harmonic oscillators. Essentially, because there is always some subtleties with the field, with the infinite degrees of freedom. To compute the energy, etc., one has to be careful. But for most of the task, this is going to be the quantization of harmonic oscillators. And if you are bothered by the friction term, don't worry. The friction term can always be eliminated. Example: let me rescale the field phi of k by multiplying by the scale factor, and use conformal time. So change from cosmic to conformal time. Then it's a simple exercise to change variables in this equation. And the equation that you get is phi prime prime, conformal time second derivative, psi, and there is no psi prime. So we have eliminated the friction term with this change of variables. So therefore, this is an harmonic oscillator with a time-dependent frequency. This is the frequency. There is a missing parenthesis here, by the way. And so this is what we are going to do: quantize all these independent oscillators. And here, you know, just one thing before we have a rest. From here, you understand why Xi, remember Xi was the coupling to the curvature. Was, oops, sorry. I don't know what I did. Here I am, sorry. Xi, it is in this first equation, is the coupling to the curvature. If you put, there is a parenthesis here, just after the 1/6 that I missed, sorry, there is a typo. So if Xi is 1/6, this term vanishes. And so if Xi is 1/6, the field doesn't see the curvature. This is why it's called, you know, sorry, one more thing. And if you put the mass equals 0, you know, both things, mass equals 0 and Xi 1/6, then this term cancels and this term cancels. And this is like a time independent harmonic oscillator. So in that situation, that is called the conformal coupling, the field doesn't see the curvature. The field lives like a Minkowski spacetime because you have a bunch of time-independent harmonic oscillators. And the reason, this is why we call that choice m equals 0, Xi equal 1/6, the conformal coupling, because it makes the field to fill only the Minkowski part of the metric. The metric is conformally flat, so we remove this conformal part, and the field lives like a Minkowski spacetime. So again, that happens only in the conformal coupling case, 0 mass, Xi 1/6. And so I think this is a good point to have a break. If you have any question about this part, go ahead. Probably this is familiar to most of you, but in case it is not, you can ask me now.
There are no questions in the chat so far.
Okay, so then let's have a break of five
minutes. Okay, so 5-minute break. Answer at the beginning or at the end, as you wish.
Right, so there are a few questions. One is, I remember R vanished in the last slide. I don't know exactly where you are referring to. Let me address the last question, which is related, and maybe that will be clear. So the last question is, what is the physical reason behind the addition of the coupling between the field and the curvature? You know, why in the field equations we introduce this extra term? And the reason is that, you know that the Klein-Gordon equation in Minkowski spacetime can be derived just from Poincaré invariance, or from the Poincaré group. So the question is, now imagine you want to generalize that to a curved spacetime. What is the most general generalization that you can build? Of course, you know, the box operator knows about the metric. So you need to replace the flat box by the curved box. But you are also allowed to add terms which vanish in Minkowski. So just for generality, we include these terms because otherwise we are restricting ourselves. So this equation with this term is the most complete generalization to curved spacetimes. And different fields in nature may have different couplings, and we don't know. So if you want to describe a general scalar field, you need to include it. Some field theories assume a minimal coupling, you know, just 0, Xi, others don't. So that they are different field theories. So different scalar fields may have different couplings to the curvature, at least theoretically. The Higgs boson, which is the only scalar field that we know. We don't know what is the coupling because we have only proved it in the lab with very low curvature, but it could have some coupling. We just don't know, and we don't know any other scalar field. So I don't know if can psi be related to the Mirchi parameter? I mean, the Mirchi parameter appears in loop quantum gravity, so that is a completely different business, and so it could be, but it has a completely different origin. This psi, this coupling is just, as I said, a way to write the most general scalar field theory. And I don't know if I have addressed all the questions.
You can go ahead.
Okay, if there are more questions, please,
presentation.
please don't hesitate to ask because we have some time. Okay, so therefore, because as I just said, the theory of a scalar field in FRW, FLRW, is like equivalent to infinitely many time-dependent harmonic oscillators. And we know that for a single time-dependent oscillator, there is no preferred representation. So if we have infinitely many of them, even worse. So no preferred quantum representation, just from what we have discussed so far. No preferred vacuum and notion of quanta. And that is true even if we have 6 killing vector fields. And I will show you in a second that there are infinitely many different representations respecting these 6 isometries. So these 6 killing vector fields are not enough at all to single out a preferred vacuum. Except in one situation, one very special situation. Conformal invariant fields. If you put the conformal coupling, then all the curvature terms disappear and you have a time-independent oscillator. So the statement is that a conformally coupled field in Friedman-Lemaitre-Robertson-Walker, especially flat, has a preferred representation. And the vacuum is called the conformal vacuum. But this is very special. This is only true because Friedman-Lemaitre-Robertson-Walker is conformally flat. So in general, and for other couplings, as soon as you have mass, you don't have, or psi different from 1/6, you don't have a preferred vacuum anymore. So every time you read a paper in cosmology and the paper speaks about vacuum or particles, just be alert because there is a choice implicit. It's not it's wrong, it's that there is a choice and other people may have different choices and there is no preferred choice. Okay, so to quantize, we are going to follow our program. Take the classical phase space, but we are going to take advantage that different Fourier modes do not evolve, do not talk to each other. They evolve independently. So the phase space is just the sum of many phase spaces. We complexify it as usual, and elements of the phase space, a general element of the phase space will be labeled by a label K. So K is now the equivalent of our label I before. You know, we have, this is the label of our elements. And the X dependence will be an exponential because we are doing the Fourier transform. So this is the way we are going to decompose the phase space elements. And the rest, the other part, is X independent, and we'll have the 2 entries, one for the field and one for the conjugate momentum. And they are just complex numbers in the complex phase space. So this is the form of a generic element of the phase space. The symplectic product, the same, you know, exactly the same definitions. If you give me any elements of the phase space of this form, this is, you know, imagine, sorry, there is a typo here. This shouldn't be a K here because I am summing. So this is the most general. With the sum is the most general. There is no K here. There is K if I focus on one of them. So that this K is a typo. So let me take two of these K modes and take the Klein-Gordon product. So the symplectic product is sometimes also called Klein-Gordon product. Then if you do the analysis, I mean, this is really a half a line calculation. You are going to have there is a volume that appears because of the spatial integral, and then field momentum minus momentum field, the symplectic product, you know, QP minus PQ. And the integral in X becomes a Kronecker delta of K1 and K2. So very important, even at the level of the symplectic product, different Ks are orthogonal to each other. So this confirms that they are just quite independent. Okay, the quantization, as I said, reduces to quantize a system of independent complex oscillators. And the only thing we need to remember is that these are complex oscillators. So we know how to quantize that. Again, focus on one K at a time. Choose a complex structure on the phase space of each K. Or equivalent, choose a splitting in positive and negative norm subspace. For a given K, the phase space is two-dimensional, just one oscillator, so it's two-dimensional phase space. Two complex dimensional because we are in the complex case. And therefore, gamma plus and gamma minus are just one complex dimension. So choose a complex structure or a decomposition in the way we have explained. Let's now consider a basis inside gamma plus. It's just made of a single element because gamma plus is one complex dimensional. So just choose some complex number for the field and some complex number for the momentum. And make sure you choose it normalized because we need that later. So this is a basis of gamma plus. Very simple, just a single element in the basis. Let AK and A dagger K be the annihilation and creation operator associated with this element. Because the element is normalized, they satisfy the algebra of creation and annihilation variables. The representation for the operator value distribution is just phi of K, and pi of K is just the basis, A, the basis, A dagger. As for the harmonic oscillator, with the only difference that we need to remember that these guys satisfy some reality conditions. That if we take the dagger, a minus sign should appear. And that implies that we need to put here minus K and minus K. So this is the only change we need to introduce because the field is not, this phi of K is not real. So this is the difference with respect to the harmonic oscillator, these two signs here. Again, this is needed for the dagger to be equivalent to put a minus sign in the K. So this is what I have here, sorry. Very good. Okay, dynamics. Again, just replace the basis modes by the time evolution. Take the solution to the classical equations of motion that I wrote before with initial data given by the basis modes. And at this point, we can focus on the field only because the momentum is just the time derivative of the field if it is time dependent. So we can work with solutions. The Fock vacuum is the state annihilated by all the annihilation operators as before. The Fock vacuum is fully characterized by its covariance matrix. And all components of the covariance matrix can be obtained from the field component because, as I said, the momentum components can be obtained by taking time derivatives. So this 2-point function, or if you symmetrize it, that is trivial because this is already symmetric, contains all information about the Fock vacuum. And again, the fog vacuum is selected by your choice of basis I wrote before. Let me go here to the previous slide. You choose a gamma plus, or equivalently, you choose a basis element with positive norm, and this is what defines your fog vacuum. And you can see that all properties, every single physical property, can be extracted from this quantity, which is just the first element of the basis you have chosen squared. And again, the momentum is obtained by time derivatives. And there is k minus k here rather than kk. So there is a missing prime here. It should be k prime equal to minus k. Sorry, typo. And this is because the field is complex. So if you want to determine all properties of the vacuum, just compute this simple quantity, which is completely trivial. Cosmologists like to encode this information in a quantity called the power spectrum. The power spectrum is just this quantity times some normalization factor to have appropriate dimensions. But the power spectrum, which is very easy to compute once you give me your basis, just the field part square, that's it, times this factor, that completely characterizes the 2-point function, so the covariance matrix. Therefore, if you give me the power spectrum for all case, I have full information about the vacuum. So this box completely characterizes the properties of your quantum state, and at any time, because we have already evolved in time. So the power spectrum, again, completely characterizes the properties of the vacuum and its evolution. And it is the quantity that early universe cosmologists compute. So if you do cosmology, your advisor will ask you to compute the power spectrum. And now you know why, because the power spectrum contains the information of the covariance matrix of the vacuum, and because the vacuum is a quasi-free Gaussian state, that is precisely all the information in the vacuum. If you give me P of k for all k, I can answer every single question you want to ask to the state. Symmetries in the vacuum. So let me come back for a second to space-time fields, fields in a space, not in Fourier space. Because you know that as I just mentioned, if you give me the covariance matrix, which can be obtained from this by symmetrizing, I have full information about the vacuum. So because it's a quasi-free Gaussian state. Therefore, it happens that looking the form of the 2-point function tell us what are the symmetries of the vacuum. So if you ask me, Ivan, I have this vacuum state, can you tell me if it is invariant under rotations? I say, of course. I compute the 2-point function and I see if the 2-point function is invariant under rotations. If it is, the vacuum is invariant. Again, because the 2-point function fully characterizes the vacuum. So let's do it here. Let's consider this family of possible fog vacua in cosmology and see what are their symmetries. So this is given by the power spectrum. And now we have the exponential because I came back to position space. Just because I want to see the symmetries in space, not only in Fourier space. But if you look at this, the two variables are x and x prime. This quantity, is automatically, and phi of k is your choice. Your choice of phi of k determine the vacuum, which vacuum you consider. But I see here that no matter which choice of phi k you make, this quantity is invariant under translations. Because it only depends, it depends on x and x prime, but only through the difference. And the difference is invariant under translations. So all fog vacua constructed in this way are automatically homogeneous. homogeneous, invariant under translations, just because the symmetry is manifestly displayed in the 2-point function. So the reason is Fourier analysis. Once you do it, once you build the vacuum as we did it using Fourier expansion, automatically the vacuum is invariant under translations. What about rotations? Rotations, in the exponential, we have a spatial dot product. And spatial dot product are invariant under rotations. So the exponential is invariant under rotations. However, we have here k vector dependence. So this part is not invariant under rotations. So the 2-point function, the vacuum is not invariant under rotations, unless we choose the same phi for all directions. So if you are careful enough, and when you choose your complex structure or your basis, you make sure you choose the same no matter what direction of k is, then your vacuum will be rotationally invariant. So they are isotropic, invariant under rotations, only if we choose the basis vectors to depend only on the absolute value of k and not on its direction. So if we choose phi of k to depend only on the absolute value and not in the direction, we respect isotropy. And this is natural because the equations of motion do not depend on the direction either. The different Fourier modes follow exactly the same equations regardless of the direction. Only k squared appears in the equations of motion. So that is very natural. So therefore, we find that homogeneity and isotropy do not determine the Fock vacuum. There are infinitely many different choices of homogeneous and isotropic vacuum. They differ by the value that you assign to phi of k or the power spectrum. So this is a proof that even though we have 6 Killing vector fields, they do not determine the vacuum uniquely. There are infinitely many choices. So homogeneity plus isotropy happens if the complex structure, gamma plus, or the power spectrum, the covariance matrix, do not depend on the direction of k. But still, we have infinite freedom. Infinite because we have infinitely many k's. Example. Massless field in de Sitter space. This is the question that Arianda was asking me before. What happens in de Sitter space? I call it FRW de Sitter space because de Sitter alone is bigger. De Sitter alone, remember, in fact, has special compact slices. Spatial is a 3-sphere, and Friedmann-Robertson-Walker flat is a 3-dimensional flat R3. So, however, half of the de Sitter space is isomorphic to this concrete FLRW spacetime. So consider FLRW spacetime in which the scale factor is this exponential function of time, where t is a constant. H is a constant. I call it H because this is precisely the Hubble rate, which is a constant. If H is a constant, it's a matter of half a line to check that the curvature, the Ricci curvature, is given by H squared, 12 times that, and it's also a constant. So the Ricci scalar, 4-dimensional Ricci scalar, is a constant. Of course, spacetime is especially flat. So the 3-dimensional curvature is 0, but the 4-dimensional curvature is not 0 and is constant. In this particular spacetime, because this peculiar form, there is an extra Killing vector field. Full de Sitter has 10 isometries. Full de Sitter is maximally symmetric, but half of it only has 7 isometries. Because, out of the 10, we can only keep those that respect that section of the Sitter space, that leaf invariant, that corner that is normally called the Poincaré patch. So, and there is only one extra. So in Freeman Robertson Walker de Sitter, we have translations, rotations, and this combination of translation in conformal time and you know, with this factor and these conformal translations in space. This is also a Killing vector field for this concrete scale factor, and you can check it just explicitly. And I don't have time to prove it, but one can prove that this extra Killing vector field, even though this is not globally time-like, it's only time-like in a region, whenever the first term dominates over the others. Whenever the partial eta dominates over partial x, partial is much bigger, then it is time-like. But that doesn't happen in the entire space-time. However, this is enough to select a preferred vacuum. I don't do it, but that can be done easily. And that preferred vacuum is called the Banach-Davis vacuum. So in this case, we have a preferred vacuum. One has to be careful that the massless limit has an infrared divergence, but there is a way to taking care of that. And that was derived in the 80s by Bruce Allen. So leaving aside this subtlety in the massless case, we have a preferred vacuum in this concrete spacetime. It's called the Banach-Davis vacuum. And this is useful because inflation is very similar to this. So there is some preferred choice in inflation. The Banach-Davis vacuum is selected by this concrete phi of k. You know, for each k, the same no matter the direction. So it's going to be isotropic. This concrete combination of k's, h, and a. And the momentum can be. So these guys span the positive norm subspace. And the conjugates span the negative norm subspace. And therefore, they define a complex structure and a vacuum. And is fully characterized by these mode functions, the Banach-Davis modes. And you can compute the power spectrum, and as I said, that completely characterizes the state. I wrote it as a function of k vector, but it actually doesn't depend on the vector. It's only a function of the absolute value of k, because it's isotropic, times this factor. And this is the explicit form. And
there is a short question.
Please.
Is the Banach-Davis vacuum, does it requires conformal coupling?
No, this is for a minimally coupled case. There is an extension to any coupling. So for any coupling, there is the Banach-Davis vacuum. I am doing it for the minimally coupled case here. So sorry, I didn't mention it, but this is for a massless minimally coupled field, this concrete form. Otherwise, rather than these modes, you have Hankel functions. In fact, this is a Hankel function for a specific value of the index, but for general mass and general coupling to the curvature, the Hankel function is not so simple. So this is the power spectrum. And let me take two limits here just to show you what. So this power spectrum depends on k. K is the comoving wave number. So remember, comoving is coordinate. It doesn't change in time. The physical wave number is k over a, and the Hubble rate. So let's take the limit to early times. You know, you have this Freeman Robertson Walker de Sitter, and you go to very early times where the scale factor is as small as you want. Then the one term in the parentheses dominates over the second term. And then the power spectrum is just given by the term 1. But this, if you look at this, is k over a. So this is the physical wave number, k over a squared. So this is the physical wave number by 4 pi squared. But this is exactly what you would obtain in flat spacetime. So at early times, the power spectrum looks identical to what you would obtain in flat spacetime. However, if you take the other limit, late times, then the second term in the parentheses dominates. K squared cancels with the K squared outside, A cancels with the A, and you have H squared over 4 pi squared. The physical wave number has been replaced by the Hubble rate. So at late times, the power spectrum is K independent, doesn't depend on K. You have exactly the same covariance metrics, no matter which K, a longer wavelength or shorter at late times. It becomes a scale independent, people call it. So this property, K independence, is in cosmology is called a scale invariant. And it's also time independent. So it doesn't evolve in time anymore. And the picture to think about that is the following. Imagine we are in Freeman, Lemaitre, Robertson, Walker, de Sitter. Time goes vertically. The scale factor expands exponentially. We have the Hubble radius, which is the inverse of the Hubble rate, which is constant because H is constant. And here we have a wavelength, which is associated to a wave number K. At early times, that wavelength is very short compared to the Hubble rate. In that case, for these wavelengths, very short, the vacuum state looks identical to the Minkowski vacuum. If you prove the vacuum state, the Miles-Davis vacuum there, it looks identical to the flat spacetime vacuum. You would say, I am in flat spacetime. Not surprisingly, because you are really deep inside the curvature scale. You are at very short distances. But time evolves, the wavelength expands exponentially, and at late times, the wavelength is comparable or larger than the Hubble radius. In that case, the evolution brings the power spectrum to a constant and a scale invariant. And this is precisely the reason why cosmic inflation is so popular, because cosmic inflation is able to take vacuum fluctuations as the properties of the Minkowski vacuum that we have here in this room, and stretch them out to cosmological scales and replace the Minkowski fluctuations by very large fluctuations and time independent. And these fluctuations later on in the universe produce the cosmic structures that are the origin of the density perturbations that we see in the universe, the large scale structure. So I don't want to go in this direction because you will have a course on quantum cosmology where these things will be applied. I just want to make connection. So this is the nexus of connection between my course and Merce Martín Benito's course on quantum cosmology. This is the way, in particular for inflation, the way inflation creates the primordial perturbations. And the way we compute that is just by evolving the covariance matrix. So this is what we are doing with the power spectrum. And we see these nice physical features. This is one of the most important applications of quantum field theory in curved spacetimes. And in fact, when people look at the sky and we see galaxies and galaxy clusters and structures, as well as anisotropies in the CMB, you can say that that is a confirmation of quantum field theory in curved spacetime, if you believe that the origin is really this origin. So according to inflation, the origin of all the cosmic structures is precisely in these aspects of quantum field theory in curved spacetimes. The fact that the expansion of the universe is able to transform the covariance matrix of the Minkowski vacuum to the covariance matrix of something with large fluctuations. So in-out scenario for cosmology. So I need to speed up. So let me consider now just as a mathematical game. In-out scenario. This is just, I should go fast over this. So I'm going to skip this exactly the same as I described before.
You still have about 10 minutes before the questions.
Right, but they have another section here. So let me invest those 10 minutes describing the Hawking effect. In this section that I just jumped, I was just doing the in-out region, in-out scenario in cosmology, considering a scale factor, a fictitious scale factor, which is flat at early times and then flat at late times. You can see that art is not my strong point. I am not very good artist, but I did my best. So imagine a universe which is Minkowski, then expands, and then Minkowski. We have in region, out region, and we can ask, if I put the vacuum here, what do an observer in the out region measures? But this is exactly what we did before. In representation, out representation, Bogoliubov transformations. What is important here that I should mention is that the Bogoliubov transformations in cosmology, the alpha and beta coefficients in general should depend on the two indices, index here and index here. But in cosmology, because of the homogeneity, the index are coming from plane waves, they happen to be diagonal. So K prime, there is a Kronecker delta in alpha. And in beta, there is a Kronecker delta K minus K. So they are diagonal in this concrete sense. So they are very simple. They only depend on the absolute value of K, not on the direction, and they are diagonal. And this is important because then the Bogoliubov transformation relating in and out is precisely a two-mode squeezer. This is what people in optics call a squeezing process. And a squeezing process tells us that the in vacuum is perceived by the out observer as having pairs of particles, like this. Exponential of A, K, A dagger of minus K. So the out observer doesn't measure the vacuum if beta is different from 0, but he measures pairs of particles moving in opposite directions. This is needed to conserve momentum, by the way. So this is expected, because otherwise we will violate momentum. So particles are created in pairs with opposite momentum. This is just an application of the previous formulas. Remember, only this in-out picture, this particle creation, is only possible to talk about if there is in-out scenarios. If we don't have these asymptotic regions, we don't know what in particles are or what out particles are. So talking about particles becomes ambiguous. So that is very important. Never forget about that. This particle creation only makes sense in this very special scenario, which is not our universe, because our universe is asymptotically de Sitter, it's not asymptotically flat. And in the past, we had the Big Bang in GR or perhaps something else in quantum gravity. Okay, now the last part of my talk, the Hawking effect. 10 minutes. I cannot show you the details because the details will require 4 more lectures. But you had a course on black holes already by Alex Perez. So you know many of the things I'm going to say. I just want to focus and give you a simplified version. I mean, not simplified, just not giving you the details and tell you how the Hawking effect appears. It's going to be similar to cosmology. In cosmology, let me emphasize that one AK doesn't mix with a different K prime. One AK mixes with K and minus K. That's it. No, there is a prime here, there is a typo. That shouldn't be there, the prime. So a K mixes with K and minus K. So it's just a two-mode squeezing, a two-mode transformation. Out of the infinitely many modes, each K goes to minus K and itself. So it's a two-mode transformation, two-mode squeezing. The same is going to happen with the Hawking effect. One mode is going to be the Hawking particle. The other is going to be the Hawking partner. So particles are going to be created in pairs, exactly for the same reason. Hawking particles flying far away from the black hole, escaping to infinity, the Hawking partner falling in. But let's try to make sense of that. Good reference, Wald's book has a very exhaustive and deep, extremely deep discussion. And more user-friendly, the book of Navarro Salas, who, by the way, was my thesis advisor, and Sandro Fabri. So let me show you a simplified model of the formation of a black hole. To have Hawking radiation, you need the black hole to be formed dynamically. If you go to the Kruskal eternal extension, Hawking radiation doesn't happen naturally, but it appears naturally in the collapsing process, dynamical situation. So this is called the Videa spacetime, and this is a black hole formed by this blue line. You know, this is the Penrose diagram. We have a Scri minus, a Scri plus, and this blue line is just a spherical shell of incoming radiation. You have a shell of photons coming in, and it forms the black hole. This is what this is. Before that time, if you are here in this region, I call Mink from Minkowski, you are inside the shell. So if you use Birkhoff's theorem, you just see Minkowski spacetime inside the shell. If you are here, you are outside the shell, and the spacetime is Schwarzschild. So, you know, in this way, you know, there is a discrete jump from Minkowski to Schwarzschild because we have a thin shell. If in a realistic situation, the shell is not thin, you know, it has some profile. So you go smoothly from Minkowski to Schwarzschild. And, you know, this is the event horizon that is formed. And, you know, we have always this funny situation that the event horizon is formed even before the shell collapses. So you are in Minkowski spacetime, zero curvature, and you have an event horizon. I tell you this to make you think how, you know, this notion of event horizon is really global, too global in my opinion, and it even appears in a region where curvature is zero. You are in Minkowski spacetime because a shell will collapse in the future. So the event horizon knows that a shell will form in the future. So if you are here and you try to escape, you are not on time anymore. You will never be able to escape. Anyway, so you know, Scri minus, Scri plus. We have coordinates in Scri plus. U out is the coordinate along the Scri plus. U minus, V out is the coordinate along the Scri minus. And I'm going to call V out the coordinate along the horizon. And this is an in-out situation because we have a flat spacetime in the out in the Scri plus and flat in the initial. So we are gonna ask in-out questions. In region, Scri minus. Out region, Scri plus together with the horizon, because otherwise Scri plus alone is not a Cauchy hypersurface. So we need also the horizon. And we are going to prepare the state here. It's going to be the Minkowski vacuum. And we are going to ask what out observers perceives in the out region. The relation between them, you know, the key mathematical is the relation, you know, I am not deriving this. I'm just telling you that the key aspect is to pay attention to null ray evolution, to the evolution of null rays. So imagine you emit a null ray from this point in a Scri minus. The null ray will be reflected at r equals 0 and will reach Scri plus. If the emission happens here, it will go here and will die in the singularity. And you know, you see here that there is a relation between the departing point and the arrival point. V in will go by propagation to U out, or V in will go to V out, depending if you are in this part or you are in this part. That relation is all what we need to derive Hawking radiation. So let me first tell you what the relation is between V in this region and V out. That is given by this complicated relation. U out, the arrival point, is given by the initial point by this expression. If we go to the second part, the part that goes to the inside the black hole, then the relation is way simpler. V in goes to V in. There is nothing. So V out. V in goes to V out. So that is the relation between departing point and arrival point. Of course, Hawking radiation appears because this second one is interesting, is non-trivial. And here we can do two limits. One is when the departing point is in the remote past, very close to minus infinity. Here, then in that case, when V in goes to minus infinity, this term dominates over the log because the first term grows faster than the log. So at early V in, the relation is U out similar to V in. So that means that if you emit a photon here, goes here, and arrives here, and there is no blue shifting or red shifting, the time levels are linearly related. So the photon arrives with no change. However, if the photon is emitted close to the formation of the horizon, it will suffer a huge redshift because it needs to climb up the gravitational potential and to escape the black hole. Then the relation between in and out is given by a log. And this log is the redshift. And this will be the cause of Hawking radiation. This logarithmic redshift is what causes Hawking radiation. And you need a black hole for that. And kappa, I didn't mention it, sorry. Kappa is the surface gravity, but you probably know what it is after Alex's course. So let me just tell you what happens with the Hawking effect. In basis is the basis that chooses the in representation. And it is labeled by three numbers: the frequency, L, and M, which are angular numbers. And the reason is because, Schwarzschild is spherically symmetric. So here is better to work in angular space than in Fourier space as we did in cosmology. So in modes are just plane waves in the V part and spherical waves in the angular part. So these are just what defines the Minkowski vacuum in the in region. And these are plane waves, but we normally work with wave packets because plane waves are not physical in these non-compact slices. So imagine I'm going to work with S, but I really mean wave packets, just packets made of them, which are localized both in frequency and in position. Out basis, so we have the analog plane waves selecting the Minkowski vacuum in Scri+. And for the horizon, because the horizon is not flat, and in fact, geometry is changing, we don't have a preferred basis. But a preferred basis will appear in a second through the Hawking effect. So let me just leave it unspecified. Choose whatever you want at the moment. This is the in representation, producing the in vacuum, and this is the out representation. So what I have to do is to take the in modes and propagate them to the out region. It happens that this, in practice, is easier to do the other way around. It doesn't matter for the calculation, but it's easier to take the out modes and bringing them back in time and compute the Bokoliubov coefficients. It's just simpler. And you can see Hawking's paper to convince you why. So what I'm going to do is to take the the out mode in Scri+ and propagate it backwards in time to Scri-. And then write it as a combination of the in modes and the complex conjugates that will define the Bokoliubov coefficients. But I find a difficulty because it happens that a mode out with well-defined frequency in the out region, when propagated backwards in times, give us a combination of in modes with all possible frequencies. In fact, this omega here should be an F. That is the frequency of the in mode. That is a typo. That should be an F, and I am summing over F. So what I want to tell you, is that if you propagate the out modes just blindly back in time, you are going to get an infinite combination of all frequencies in the in region. So you don't go to a single frequency. A single frequency out goes to infinitely many frequencies because frequency is not conserved because the space-time is changing in time. So this is a mess because, this is not a two-mode to two-mode relation. This is a one-mode to infinitely many modes relation. So this is complicated. But there is a trick. And the trick is to change bases in the in modes. There is a very smart trick. So I'm going to tell you the trick, and I'm not going to derive it. So you need to believe me. So consider, rather than the out mode, consider the following wave packet. So consider a packet, wave packet in the out region and a wave packet in the horizon. This int should be horizon. I am mixing the notation. But consider a wave packet in the horizon, which is obtained from the out one by a reflection. Let me tell you how to do that. This picture, go to Scribe Plus, consider a wave packet there, center at some U out. From it, I'm going to build a wave packet in the horizon, which is obtained by the following reflection trick. Propagate back in time. You arrive here, and whenever you arrive, you reflect symmetrically respect to the horizon formation time. And then go to the horizon, and that is the wave packet I am calling as int. This is the reflection trick. Consider this, consider this two, and you will see why, and you are going to see in a second why this two. So this out mode and the reflected mode in the horizon in this concrete manner. It happens that if you consider this linear combination of this out and reflected in conjugated with this concrete coefficient, this concrete combination, when you bring it back to scribe minus, it has positive norm in the in basis. And if you interchange the roles of int and out, this also have positive norm in the in basis. So what I am telling you is that the evolution is really two-mode to two-mode, but we initially started from the incorrect in modes. So if you choose other in modes, these ones, it is manifest that the evolution is two-mode to two-modes. So conclusion, the transformation, I am not proving why, but one can prove it. The transformation is way simpler if you use F and 1 and 2 as the in basis, one for each frequency, of course. And then the evolution from in to out is two-mode squeezing. It's precisely a two-mode squeezing, where the beta and alpha coefficients are related by the coefficient that appears in this expression, the exponential of pi omega kappa. So in summary, and I am about to finish, one more minute and I am done. The Hawking effect is a two-mode squeezing process, and that is manifest if you choose cleverly your basis in the in region. And this two-mode squeezing is characterized by alpha and beta Bogoliubov coefficients, whose ratio is given by this factor. And this is all what I need. Now let me derive the Hawking effect from this factor. This is all what I need. So this is a very special two-mode squeezing. Why? Let me compute for you the particle number that the out observer will measure in the evolution of the in vacuum. You know that all what we have to do is to compute beta square from before. Let's compute beta square starting from the following three. Remember that there is a normalization condition for alpha and beta. Alpha and beta needs, for the evolution to be symplectic, they need to satisfy this, this relation. This is always true for any Bogoliubov transformation. Now let me divide by beta square. So in the first term, I have alpha by beta. In the second term, I have 1. And in the last term, 1 over beta. Now let me use the ratio between alpha and beta I just derived. So the first term becomes the exponential of plus, because this is the inverse of this. Twice that because the square. So exponential of 2 pi omega kappa minus 1 over beta. Now invert this relation. Beta square, which is the particle number, is precisely 1 over this. But you recognize here the Bose-Einstein thermal equilibrium distribution. The state as measured by the out observer is precisely a Planckian spectrum. It's precisely a thermal spectrum with temperature given by kappa by 2 pi. So this proves that the in vacuum evolves to the out region. I mean, evolves to the horizon and to the out region. And it happens that the evolution is a two-mode squeezing. Particles are created in pairs of Hawking particle going to the out region and the partner going through the horizon. And if you look the spectrum of the out particles only, the part going to Scri plus, it is precisely Planckian. Of course, I am neglecting gray body factors produced by the evolution. I am simplifying a little bit, but this is the key part of the Hawking process. So the black hole is a squeezer, two-mode squeezer that takes the vacuum and creates pairs of quanta, each of them with a Planckian distribution in frequencies. So magically, we can associate a temperature to the black hole, because if you are outside, you see that the black hole emits, starting from the vacuum, it emits thermal radiation with a temperature given by the gray body factor. I am finishing, Pierre, sorry.
Thank you very much, Ivan.
Just 1 more minute and I am done. So let me just finish this by putting some constants, h bar, c, and the Boltzmann constant, because this formula for the Hawking temperature is one of the most beautiful formulas ever. If I introduce back all the constants, you have h bar, c, g, and Boltzmann constant. In a single expression, you have all quantum mechanics, relativity, gravity, and statistical mechanics in a single expression. So it's difficult to find a richer expression in physics than this. And this comes out from the Hawking effect. I imagine that Alex emphasized this a lot, but I just want to emphasize it further. The black hole loses mass because it emits radiation and eventually will evaporate. Conclusion. So, I have given you this interplay between mathematics and physics, a formulation of a theory based on geometric objects, color structures, which are clean conceptually. And if you like geometry, I'm sure you love this construction. But together, producing really outstanding physical predictions that tell us that, particles can be created out of the vacuum, black holes can emit radiation, and you can create the cosmic structures starting from vacuum fluctuations. All that is coming from this interplay between geometry, quantum mechanics, and physics. And if I have to communicate one message in this short mini course, this is the message. The rich and beautiful interplay between geometric structures, quantum mechanics, and physical predictions. So let me stop here, otherwise Pierre is gonna kick me out, and I am open for questions.
Thank you very much, Ivan, for your course. We are just 3 minutes over time, so it's perfectly fine. If people have questions, then I think we can take the time. I know that there were some questions which were postponed during the course. So you can raise your hand, or I will.
I see two.
Yes. So first, Melissa.
Hi. So my question is regarding this arbitrariness in the vacuum. So for instance, I am just comparing this scalar geometry with the geometry of generalized geometry, which is kind of similar in the sense that you have like a similar structure, but you don't have the symplectic structure. And instead of having a complex structure, you have that j squared is equal to 1. But the geometries are very similar, and actually they are related in some physical context. And in generalized geometry, there is like a kind of arbitrariness coming from the fact that you want to study like Riemannian generalized geometry, and then you have Levi-Civita connections that are, instead of having one unique Levi-Civita connection, you have an affine space of Levi-Civita connections. And this arbitrariness comes from, I think, and I think that's the hint, that it comes from the fact that there is still not a good understanding of a principal fiber bundle structure coming from this geometry, or from the fact that the torsion and the Riemann tensors are given by hand. So my question is, I know these are different contexts, but kind of similar at the same time. My question is, this arbitrariness can come from a very deep geometric reason, like the ones that I'm giving. I know it's different context, but the arbitrariness is somehow related to the geometry, to the Scalar geometry.
Right. I mean, the arbitrariness is you know, it's conceptually similar. I fully agree. It's a very, very nice comparison. But I mean, that is not a surprise, right? Because every time you generalize your mathematics, adding new structure, there is new freedom that you introduce. And unless there is any way to determine that freedom uniquely, the freedom remains and persists. So it happens in generalized geometries, it happens in Scalar geometries, etc. And the question is, you know, is there anything we are missing? Maybe that is also part of your question. Can this arbitrariness be just a lack of knowledge from us, or is really fundamental?
That's my question.
Right. So is there something that we don't know? There is a theorem, it's called Ivan's theorem, that every person working in quantum field theory has proposed a preferred complex structure, a preferred vacuum. Even myself, I am not an exception. So, you know, we all have the same questions, and we all have tried and have, you know, trying to look for, you know, what can define a preferred one. Even when I myself have proposed some concrete ones in some concrete scenario, in cosmology in particular, my opinion is strong, and is that the ambiguity will persist. There is an inherent ambiguity here, and unless you introduce new physics, new symmetries, new, you know, you go to quantum gravity and you introduce new structures, with just quantum field theory on a globally hyperbolic, generic globally hyperbolic spacetime, my strong opinion is that there is no a preferred way to select one, that we are not missing anything. Maybe somebody will prove me wrong. That will be excellent. So at this point, that is my opinion.
Okay, thanks.
No problem.
Thank you. There is another question by Ariadna.
Hi, thank you very much for the nice talk. I wanted to ask about the Penrose mechanism, if it has been formulated in the language of fields.
Yes, that is called super radiance. You mean the Penrose mechanism of extraction of energy by rotating black holes?
Yes, exactly.
Yes, that is called super radiance. If you emit a wave to a rotating black hole, you can get back a wave with larger amplitude. In fact, this super radiant phenomena trigger Hawking radiation, trigger people thinking about Hawking radiation. Because this is like a stimulated process, right? You illuminate the black hole with something and it emits more. It's like a stimulated phenomena. And every time there is something stimulated, quantum mechanics brings the spontaneous counterpart. So the Hawking effect can be understood as the spontaneous counterpart of that. What people were really surprised is that the Hawking effect happens even for non-rotating black holes. Not only for Kerr geometries. But just coming back to your question, yes, there is a wave analog is called super radiance.
Thank you very much. I will check it.
Thank you. Another question by Xian Kai.
Thank you for your lecture. I have a question regarding to the isotropy of the scalar field in FLORW universe. You said that the symmetry is the vacuum is only isotropic when the Fourier modes only depend on the absolute value of the wave numbers. So I'm wondering if the Fourier modes is anisotropic. It also depends on the direction of the wave number. Would that, how to say, destroy the isotropy of the underlying geometry? Is that FLRW metric is not valid anymore?
Right. So the question is the following. He's asking that as in Freeman, Lemaitre, Robertson, Walker, if we choose the complex structure, or to not depend on the direction, but only on the magnitude of K, then the vacuum is automatically isotropic. So he's asking what happens if we relax that condition? Can we consider Fock vacua, which are not isotropic? And would that be incompatible with the background geometry, with the isotropic geometry? And then we have to distinguish two regimes. The regime in which we are working, we are neglecting back reaction. So we are declaring that the energy in the quantum field is insignificant to produce any change in the geometry. So the geometry is not modified by the presence of the field. Then in that case, of course, you are able to say that your vacuum is not isotropic. People will ask you, why? I mean, your space-time is isotropic, and you choose a state, a Fock vacua, which is not isotropic. But you can say, because I don't like isotropy, and I define it in this way. But then it's perfectly fine. Your state is a quasi-free Gaussian state, which is not isotropic, and the space-time doesn't change because you are neglecting back reaction. But this is an idealization, right? Back reaction always happens, even if it is small. So the statement is that what you are doing is introducing some anisotropic matter, and that anisotropic matter will change the metric slightly, but will change it and will make it a Bianchi metric, an anisotropic space-time. So again, the energy in your not isotropic quantum state will slightly change the geometry and introduce anisotropies. You are putting by hand anisotropic matter, and the Freeman Robertson Walker doesn't exist if you have anisotropic matter.
Thank you.
Thank you. And still a question by Geet Chandra.
Hi, this is just a follow-up question from earlier. So you said that the psi-r term you added to the Klein-Gordon equation. It sounded like it is a term that someone has put in by hand, or is it derived from equations? Or if it's put in by hand, can we add terms like f of r, like more higher order corrections to the Ricci scalar?
Right. So it is by hand. It is just because if you are a theorist and you say, okay, I'm going to write the most general scalar field theory I can write, then you have to include it. Otherwise, you are restricting ourselves. And the statement is that with this coupling, if you have gravity and matter, the Einstein equations are still satisfied. You know, if you put now gravity and you derive the equation of motion for gravity, with that term, you still have G mu nu equal to the energy momentum tensor. If you introduce f of r, that changes. Then you are out of Einstein gravity. So the statement is that for a scalar field, and if you want to keep GR, the same gravitational theory, then this is the most general action that you can write. If you have other fields like vector fields, etc., you can include Riemann and Ricci's, etc., because you have indices. But for a scalar field, the most general thing you can do is to for a standard Einstein gravity with no torsion, nothing, just vanilla GR, then this is the most general action you can write.
Got it. Thank you.
Thank you, Ivan. Before we close, I can't help asking a question myself, if you don't mind, which is maybe a bit more philosophical on your motivations. In particle physics, we also have in and out states, but the main difference with cosmology is that when we are in the lab, we can control the in state, and then we observe the out state, and this is our way to test the theory. In cosmology, it seems that the only thing that we can do is observe the out state, but we don't know anything about the in state. And so you've made very clear in your course that there were many possibilities to choose a vacuum state. But my question is, why should it even be a vacuum state and not any random state?
Thank you. This is an excellent question. In fact, many of my work has been dedicated to exactly to that question. Because once you get rid of the notion of preferred vacuum, then the question is what the initial state should be. So the standard paradigm is this theory of inflation, in which people say, you have inflation for some time. You have the space-time is like the zeta, so wonderful. In the zeta, you have this extra isometry, and there is a preferred state. So you choose the Weiss-Davis vacuum, and out of it, you derive things. So this is what somebody in love with inflation will tell you, and there's a good point. In that case, you have symmetries, and then you can say that there is a preferred initial state. But if you pay attention to the details, you say, wait a minute. Inflation is not the origin of the universe. Something happened before inflation. And in fact, when we speak about inflation, we only make statements about the patch of the universe that we can see. We don't make statements about the entire cosmos, because inflation has to emerge from somewhere. So, question: do we really have, global de Sitter symmetries to select a preferred vacuum? Maybe not. Second, what happens before inflation? Who tells you that whatever happens before inflation didn't create particles and you reach inflation in a state that is not a vacuum? If you try to put inflation with pre-inflationary physics, then choosing the vacuum may be over restriction. So the question is, what happens what would we see in the sky if the quantum state at the beginning of inflation was not the vacuum, but was something different? And if it is something different, what it should be? And I think this is precisely the goal of Merce Martin Benito's course on quantum cosmology. We can use quantum cosmology to provide a picture of what happened before inflation and trying to derive what the state would be. Put the vacuum, in the past, in the Big Bang, or in the bounds, or whatever theory you have. So can we use quantum gravity to derive the state at the onset of inflation, rather than assuming that it was the Banach-Davis vacuum? And the important thing is that whatever the state is, we could see some imprints in the sky today. In fact, my strong belief is that the most promising way to test quantum gravity is looking at the CMB, because that may have traces of what the vacuum state was in the past, what concrete state we had. So your question is completely correct. In the absence of this preferred notion of vacuum, we are opening the box. And we don't really know what state we should have. So let's look at the sky. Let's put our physics hat, look at the sky, and try to learn what the state was by looking at the CMB. I think that is completely fascinating.
Thank you very much, Ivan. Thank you once again for your time. And thank you all for the attendance.